potential.
Yes, okay, so let's perhaps look at that. The question is, now I have a break in the derivative. At x is equal to 0 and at x equal to a. So let's discuss that a little bit. Now, if I had a potential well which has a finite potential on the outside, okay, something like this. So this still can be analyzed to some point analytically, okay, and graphically, whatever. So we'll, perhaps if we have time, we'll look at that. But so we have this well again, and suppose outside the potential is not equal to infinity, but is equal to some constant v of x, okay, or v0, I'm sorry. Now, what happens to our wave function? So suppose this v0 is very large. So this is approximately like this problem. So the changes that you are going to get are going to be, again, small. So when we solve this problem, we are going to see that if you look at the wave function, the u part, the u of x part of the wave function, again, we are going to have a sinusoidal form. So let me look at the n equal to 1 solution. But because v0 is so large, and the energy of my particle is somewhere over here, it's going to be somewhat unlikely to find the particle out here where the potential is very large. So the wave function is going to be very small. And I know that in these regions where v is larger than e, the wave function is decaying exponentially. So I'll get this u of x decaying exponentially outside. And you can convince yourselves that it will decay faster as v0 becomes larger and larger. And then the inside, it's going to be, okay, again, sinusoid. So it's going to be a more complicated problem because now I have to match these at these points, the wave function on the outside and the wave function on the inside. But it's going to be something like this. It's going to be very similar to these functions which go to 0 outside this range. Okay? But we'll have now an extent, exponentially decaying extent, which goes out like that. Okay, so in the limit, this v0 goes to infinity, this will decay faster and faster, okay? And you are going to have the solutions that we get as a limit. Okay, so that's why we have a break in the derivative, is the limit of this potential on the outside going to infinity. Otherwise, if it's finite, then we do not get a break in the derivative. Everything is nice. But of course, this is a more complicated function. So we start with the case when potential is infinity on the outside. Okay, so that's why we have discontinuity in the derivative. All right. Let's see. So now I have a bunch of solutions which look like that. Let me just put them up here again. I have this un, which is going to be normalized, and I have sine n pi over a x with a corresponding energy En equal to h bar squared k squared, which is going to be pi over a squared. There's a 2m and then n squared, so pi squared. So that's going to be our energy. Those are the energies of our system. the corresponding t of t is going to be e to the minus I over h bar, that en times t. Okay? So for any wave function, I have that. Let me just quickly normalize this because I don't want to keep carrying this a around. How do I normalize it? Well, I want to un star un dx. It's finite only between 0 and a equal to 1. It's a real function, so it just gives me 0 to a star a, sine squared n pi over a x dx should be equal to 1. So this is the integral of sine squared, which just oscillates between +1 and -1. Okay, so this sine squared is a function which oscillates between 0 and 1 and does something like this. It has to go back to 0. Okay, so something like this is a function of x. So on the average, it's just equal to 1/2. So it's just 1/2 times a. Okay, so I'm going to get a star a. Okay, you can calculate the integral with more traditional methods if you like, but that's what you are going to get. Okay, it's sine squared, oscillating between 0 and 1, a number of full periods, and that has to be equal to 1. So assuming that a is real and positive, I get a equals square root of 2 over a for all n. Okay, so that's something that we'll use every once in a while. That's our normalization. Okay, now we said that the general psi of x, yes?
So for the, as v goes to, v0 goes to infinity, we said that it decays more fast.
Mm-hmm.
Why we determine that between the a and plus infinity and 0 and minus infinity, there's a decaying function? I missed that part.
Okay, you have a choice out here. Okay, I erased the problem, but in this region, which is known as the classically forbidden region, so you have this region where the particle classically should not even exist, right? It has an energy which is equal to E, this much, and outside you have a potential energy which is larger than E. So classically it shouldn't even be there. That's the classically forbidden region. Now in that region, our differential equation has two solutions. It's either exponentially increasing or exponentially decreasing. I don't want the exponentially increasing one. Why? Because I cannot then even normalize it. Okay, I want a solution that goes to 0 as x goes to plus or minus infinity. For that reason, okay, I want only exponentially decaying functions. Okay, anything that's growing up towards the infinities makes the wave function non-normalizable, and that means the electron is not there. In fact, it has a probability associated with it which is greater than 1 or whatever. Okay. All right, so let's go back. So my general psi of xt is going to be a linear combination of these types of solutions, because all of these things, okay, this u times t, no matter what n is a solution to the Schrödinger equation. Okay, because Schrödinger equation is linear, you can very easily see that. Okay, if I multiply both sides by 5, nothing changes, right? So this function then in general, the most general form that I can have is going to be n from 1 to infinity. So I'm going to consider all possible solutions. I am going to include a Cn, okay, that's going to be the expansion coefficient. And I am going to get un of x e to the minus I e n over h bar t. Okay, so that's the most general solution that you can have. Okay? So what does this solution mean? How can I interpret this for a certain particular case? Now, remember in classical mechanics, we have this initial condition. Someone gives us the initial position, initial momentum, and from that we calculate position and momenta at later times. In quantum mechanics, someone gives us the initial wave function. Okay? So someone tells us, given psi x 0. So the problem is, what is psi x t greater than 0? All right? So now I try to find out what these Cn's, general expansion coefficients, will be based on what the initial condition is. So let me just write this down. Psi x 0 is equal to n from 1 to infinity Cn un of x. Okay, so our recipe for solving this problem will be determine these Cn's. So once I determine these Cn's, I put them into this equation and I have the general solution. Okay, so that's our strategy for finding what the general wave function is. Someone must tell me what's happening at time equal to 0 so that I can find these Cn's and then put them in here and get the general solution, how things change at time. Okay? Yes?
This solution is deterministic? Is this solution?
Well, how psi develops is deterministic, right? So if I start with a certain wave function, what happens to that wave function is well defined. I can calculate psi at larger times. But any information that I try to get out of it is going to be probabilistic. Why? Because I always have some psi. Okay, so if someone asks me where the particle is at a certain time, I have to look at magnitude squared of psi, which will be the probability density function. So the probabilistic nature of the measurement is still there, but the wave function itself develops very nice, okay? You could say deterministically in time. Okay, other questions? All right, so what happens for certain special cases? Let's look at that. All right, so okay, so what happens if I am given that this psi x0 is equal to one of these functions. Okay, so in some sense, in this expansion, only one term is there. Okay, all other CNs are equal to zeros. Okay, so this deserves a question mark. Now, let's take certain expectation values. What is first of all, okay, let's go step by step. Now, if I look at psi xt, the only thing that's going to change is I'm going to get a time dependence, n of x e to the minus I e n over h bar t. Okay. Now, if I look at psi xt magnitude squared, that's the probability density function, you see all time dependence drops out because magnitude of this phase is equal to 1. So that means the probability density function is not changing. The magnitude squared just sits there. You see, if I have even one more term there, that's not going to happen, right? There will be cross terms between the two different exponentials. Because of those cross terms, the magnitude of psi is not going to be independent of time. So this is independent of time. Similarly, if I look at something like expectation value of x, for example, what happens to that as a function of time? Well, it's going to be psi star x psi dx. But again, psi star times psi means I'm going to get the complex conjugate of this term multiplying. So the time dependence will go away. So this is going to be, again, un star x un dx. So again, independent of time. And you can just convince yourselves that expectation value of x squared, expectation value of p, expectation value of p squared, lots of things like that will all be independent of time. Okay, so after I discuss this, I'll solve an example of the case when this psi is not equal to just one term like this, but the sum of two terms. Then we'll see that these things does not hold. Okay, they just doesn't hold. Okay, in particular, let's calculate a certain special average. Okay, so what is the expectation value of H? So that's the total energy. What is the expectation value of H for something like, you see, I just introduced the solutions to the one-dimensional box, but we are doing things very generally now, so these things hold for actually any H. Okay, I just wanted to introduce these wave functions, etc., so that you can think of something concrete if you need to. But what we are doing here actually is valid, okay, after this line over here. Anything below that line is really relevant to any H, any type of solution. Okay, so what is the expectation value of the Hamiltonian? Well, again, I have this psi star of x and t, h psi x and t dx, right? So this is going to give me, x is integrated over how the average value h changes with time. And not surprisingly, that doesn't change. And I'm going to get u n star e to the plus I e n over h bar t, okay, h u n e to the minus I e n over h bar t dx. So these phase terms, the time dependence cancels out. But you see, h times un is something I know, right? H un is an eigenfunction, okay? Just like in linear algebra, we have this terminology, h un equals en un. So h is the operator, un is the eigenfunction, like the eigenvector, and this is the eigenvalue. Maybe I'll just write them down. This is the eigenfunction, and this is the eigenvalue. Okay, so this h times un is just e times un, en times un. But en is just a constant, so it will go out of the integral. And I'm left with un star un, which is normalized, so it gives me 1. And I end up with en. So that's the average value of the energy. Let's see how much the energy is fluctuating. Okay, to do that, I have to evaluate the average value of h squared. Okay, so I'll have to do the same algebra again. So I'll end up with un star e to the I en over h bar t, h squared un, and e to the minus I en over h bar t dx. All right? But if h un equals en un, h squared un is what? Yes, it's just h times h un. And since this is just en un, this is just one more operation, so it's en squared un. So I'm going to get now this thing equal to en squared. So what does that mean? If I now interested in finding what the expectation value, okay, well, what the fluctuation in h is, how much the average value of h is fluctuating. Remember, this is just the square root of h squared average minus h average squared, okay, like that. But here, both of these things are now en squared, and I get 0. So that means if the psi x0 is, okay, so for that special case, what happens, I have that, the most significant results are things are independent of time and that the energy is not fluctuating thing. Energy is definite. If you measure the energy of this object, you are definitely going to get En. There is no fluctuation in the energy. So the probability density for energy, if you like, is a delta function. You are always going to get that energy. So if a particle is in that state, the most important consequences are time independence of these quantities, one of them. Okay, so that's why we call these states stationary states. Okay, stationary means something is not moving, okay, not changing. So stationary, this is a stationary state if psi has only one of these objects. Okay. Second is that energy has a definite value En. Okay, so the eigenfunctions of the Hamiltonian give you a set of functions, eigenfunctions, which correspond to definite energy states. Now, you may not be that lucky in your psi 0. Your psi 0 is going to be given to you. So when the psi 0 is given to you, you have to determine this expansion in these eigenfunctions. And then you are going to get, obviously, various terms which are going to give you variations in these things. For one of the important consequences will be these things will be broken. So if you have a superposition of states, I'm just checking my time. Okay, we'll probably have enough time to do an example like that. Okay, so let's move on. Any questions about this piece, the stationary solutions and the results? Okay, so yes.
So, you said that we can construct the near infinite wells called quantum dots. So this property is also C there, right?
Yes, of course.
Energy levels.
Of course.
That's the special.
Yes, okay, so that's where the energy levels are. In fact, what we are going to see gradually, step by step, is that the electron may jump between these levels. Okay, so it may go from one state to another, to a different energy. And how does that happen? Because of some sort of conservation of energy, it has to absorb some photon, right? So a photon comes in, and with that energy, the electron jumps from one state to another. And later, it may just go down, and then it just emits that photon. So if you do what's known as spectroscopy, you look at light that's scattered off these things or light emitted, you find out that if you send light, certain frequencies of light will be absorbed, okay? So those will be absorbed, and you can see as those things as dark lines in your spectrograph, and you are going to understand that photons at those energies are being absorbed. So that gives you a measure of energy differences between these states. Or it may be emitted, and then you are going to get these lines, bright lines, which correspond to emission from those objects, and those things correspond to the energy released when electron goes from a higher energy to a lower energy. Okay?
Those lines will be very narrow.
Yes, well, okay, so we'll again see what the narrowness of the lines depends on how good a quantum well you have made. If your quantum well is interacting with other things, if it's hot and vibrating, size is changing, then these things are also fluctuating, and then you get your lines broadened. Okay? Yes?
Can you say that time evolution is generated by the fluctuations of Hamiltonian?
Time evolution, say that again?
Time evolution is actually due to fluctuations of Hamiltonian?
No, the Hamiltonian we assume is not fluctuating. The Hamiltonian is something that is defined by the kinetic energy term, which is, okay, well defined, and the potential V of x, which is also well defined. Okay, if V is changing as a function of time, then it's a time-dependent problem, which we have to solve differently. Then we cannot, okay, if potential is a function of time, we cannot use separation of variables. Then we cannot do any of this. So that's our second semester work, where we'll look at time-dependent potentials and how. So Hamiltonian is something fixed. It's not time-dependent, not fluctuating, etc. Yeah. Yes.
Hocam, if a stationary state is independent of time, when a wave function collapses, does that mean it stays the same and it doesn't evolve after I measure it?
Okay. Now, I have this wave function, which has actually time dependence, but this time dependence is not influencing the wave function magnitude squared. So it's not influencing average value of x or average value of p and things like that. Now, if you make a measurement, the wave function collapses and it's no longer this. Okay? A collapsed wave function corresponds to a very localized, because you have a detector now at a certain point. You have measured the position of the particle at a very precise point, and you know that the particle is there, so the wave function has collapsed to that point. So after that point, it's a different game. Okay. Other questions? All right, let's look at a case when, okay, so this was our equation. I have these UNs, etc. So let me keep.
I have a question.
Yes.
If we measure particles and which is low position, then will it collapse to one of these eigenstates?
Okay, so it depends on how you are carrying out your measurement. So the question is, will energy measurement, will it collapse to a certain point? Technically, yes, but how do you make a measurement? The measurement that you make is usually by looking at the light that comes out of your system. So you have these energy levels. Okay, E1 has certain value. Then remember E2, because of this n squared, is 4 times E1. And then you have, okay, another energy state, which is E3, which is 9 times the lower state. By the way, these things have names. This is called the ground state. This is called the first excited state. And guess what this one is called?
Second excited.
Okay, second excited state. Okay, I won't ask about the others. It goes on like that. Okay, so you have something like this, and you look at, okay, so you suppose you put this in a very hot oven so that it has very energetic, or you flash it with some light source so that the electron gains some amount of energy. So the electron is somewhere. Okay, so you don't know where it is. Now, if you see a photon coming out, so that's our puzzle. The photon comes out, and we find out that the photon h bar omega is equal to 5 E1. What happened? What has happened?
It went from E3 to E2.
Okay, so that means with this energy, it must have jumped from this point to that point. Now I know precisely where the electron is. Okay, I have actually somehow carried out a measurement, okay, by looking at this photon and determined the energy level of the photon. Otherwise, if I just try to snoop in here and try to change this potential, modify it, etc., and try to measure the energy that way, unless I am very clever, I am changing the potential, so I am changing the system. And what I am getting is not so definite. Okay, so I shouldn't meddle with the system so much. Okay, just look at what's going in and coming out. Yes?
In the EM equation, if I take A to 0,
Mm-hmm.
is there a limit where the uncertainty principle takes over and yields stuff?
No, uncertainty principle is always valid, okay, in this equation. We'll see why that is. You can still look at delta x and delta p for these wave functions, and you'll see that the uncertainty principle is still valid, okay? So
I'm not questioning the validity, I'm saying, does it cause any weird effects?
okay, the weird effect that it will cause is if you reduce the size of your well, you see the energy of the state becomes higher and higher. That is actually a consequence of uncertainty principle, because as you make your delta x smaller and smaller, your delta p is getting larger and larger. So unless your well is really infinitely high, or infinitely low in the case of the well, then the particle will escape. Okay, so if you try to squeeze the electron into too narrow a space, it will escape. Okay, so that's that. In fact, well, okay, let's not get ahead of ourselves. Yes.
I have another question.
Sure.
If we again look at the same system and see a photon with energy 15 E1, then how can we be sure whether it went from E4 to E1 or E8 to E7? In either case, energy difference is 15.
Well, okay. Let's go on a little bit more. Not all transitions are equally probable. Okay, in fact, these are important for things like atomic physics, laser physics, etc. When you are having a transition from one state to another, the two states must be related to one another by a certain symmetry relation. Okay, so you cannot. So certain transitions have very low probability and such things, because this is not a single particle problem. You have also this photon which is involved in the process, and things get a little bit more complicated. Okay, other questions?
So we can't be sure, but we can say which one is more probable.
Yes, okay. You can make additional measurements depending on the symmetry of the photon or polarization of the photon that's coming out and such things. Other questions? Okay, so what we are after is now a slightly different problem. Let me erase this bit. Okay, so suppose that I have now the electron wave function psi x0 given as 1 over square root of 2 u1 of x plus 1 over square root of 2 u2 of x. Suppose I found it to be that. Okay. Now, you can just go ahead and check that if I assign these constants c1 and c2 as 1 over square root of 2 and 1 over square root of 2, the whole thing is still normalized. Okay. That's why I choose it that way, but you can, okay, in fact, exercise. Okay, exercise show that this psi magnitude squared integral dx is 1. You can show that easily. All right. Now, what should I do? I know how this thing is developing. Psi xt is 1 over square root of 2 u1 of x e to the minus e1 I e1 t over h bar plus 1 over square root of 2 u2 of x e to the minus I e2 t over h bar. Now, let's try to find something like what is the average value. First of all, what does this wave function look like? So this is the first u1 is just the sine function, u2 is, let me draw them again. So this is u1, right? u1 of x. And u2 of x is something like this as a function of x, u2 of x. What happens when I add them up? Okay. Here I have positive and positive, so they add up. So I'm going to get a larger value. Over here, this is positive and that's negative. Okay, it's not really going to cancel or anything, but you are going to get a reduced value. So it's going to look something like this. So this corresponds to a particle more closer to the left, okay, smaller value of x. Here x equal to 0 than x equal to some other place, okay? So if I look for the average value of x, it's going to be somewhere over here, right? It's going to be to the left of the middle, okay? Left of the middle was a political slogan years ago in Turkey, okay? Okay. Then what happens as a function of time? Now, so these things have phases, and because of the phase, I cannot finish this problem this hour, so I'll tell you qualitatively what happens, and next time we'll do the algebra. So this particle now actually, because of the time dependence associated with it, I have the time dependence over there. So if I want to calculate the average value of x, now I have to put this psi star of xt, x psi of xt dx. So that will give me the average value of x as a function of time. And qualitatively, what I expect to see, obviously the average value has to be between 0 and a, because the particle is between 0 and a. And that's the midpoint. So it starts somewhere on the left and will oscillate as a function of time. Okay, so you can see that the frequency of oscillation is going to be related to this phase difference. Okay, so I have this e to the I minus I e1 t over h bar, and also e to the minus I e2 t over h bar. So you can sort of see that if you multiply these things together, you are going to get terms which look like e to the I e2 minus e1 t over h bar. So the time dependence actually goes like, okay, so if you look at this figure, something like cosine E2 minus E1, okay, T over H bar. So you see what's happening. This energy difference is the frequency with which this average value is oscillating. So this is a charged particle oscillating with a certain frequency. Okay, it will couple to electromagnetic waves, which are photons, with that frequency. That's why we are getting energy difference divided by h bar frequency photons out of this. Okay, so this is the position of the particle is oscillating. So you can think of it as a dipole oscillating near x equal to a over 2. And an oscillating dipole is always interesting for an electromagnetic field and vice versa. So that's where the source of these emission and absorption come from. Yes?
Can we construct, let's say, quantum antennas like that?
Okay, you see, this is not by itself, this is not going to radiate. The question is, can we use this as an antenna? It will just radiate photons, and in some sense it's an antenna, right? It will radiate at a frequency which is related to the energy difference, and that is usually for small, okay, nanometer size objects. It's going to be in the light, okay, the visible or ultraviolet or infrared light spectrum.
But you also understand what is the A at the last one?
A is the width of the well. The well extends from 0 to A, right? So this is point 0, that's A, okay? So I should have perhaps, okay, it's 0 to A. Okay. All right, so I'll see you Monday afternoon.